Thank you so much for coming out on this cold winter evening. It's my great pleasure to introduce Professor Donald Sadoway, who is the John F. Elliott Professor of Materials Chemistry at the Massachusetts Institute of Technology. I'm going to leave it to Don to talk to you about what he does, but I think it's important to share with you a quick story about how I know him. I studied all of my lectures in the room that you're sitting in now as a mechanical engineer, knowing nothing about chemistry at all. And then I moved to do a PhD across the road in the materials department. And my first group meeting was terrifying. Lots of words that I did not know the meaning of. So I went online, desperately searching for help, and found Don's course, Introduction to Solid-State Chemistry, available through the MIT platform. Still today, one of the best courses I've ever done. Absolutely fantastic insight and introduction to the topic. And has been watched by many tens of thousands of people around the world, which is extraordinary to think. And Don, as you will find out shortly, is an excellent communicator, and he's going to share with us his work in liquid metal batteries. So thank you very much, Don.
Well, thank you for the kind words. It's a pleasure to be here. Actually, I came here in December of 1972. I was thinking about coming here as a PhD candidate. Was shown around and went back to Canada and stayed in University of Toronto. There were some personal factors here. But I must say that the place has changed a little bit since 1972, for the better. But I've always had a very strong curiosity about Imperial College. So what I want to do today is talk about innovation and sustainability. And there's going to be at least two tracks running at the same time. One is going to be the narrative about what went on in the science, and the other is going to be about the discovery process itself. And maybe there's something transferable from what I'd learned. So why is it doing that? All right, so there's going to be two chapters, what I call tough tech. When you're working in energy, forget all the stuff that they talk about in Silicon Valley and go-go and innovation and so on. This is heavy industry. It's really hard. All that stuff doesn't apply. It's a really, really long slog. I like to begin with this image, which reminds us that electricity is tantamount to modernity. Everything that we value as a 21st century technology is predicated on the availability of electricity. And where you see light in this image, that's where you see the modern world. And where you don't see light is one of two conditions ensues. Either nobody lives there, or the place hasn't been electrified. And if it hasn't been electrified, there's nothing more important that you can give those people than access to electricity. And if you're going to add electricity here, you don't have to build a grid by gigantic power plants, coal-fired power plants, nuclear power plants. You could put solar panels and then add in the storage, and away you go. So we want to have sustainable electricity for a sustainable modernity, and that's where I want to go with this. And this is even on the charts when it comes to the United Nations. They have a 17 Sustainable Development Goals. So there it is, goal number 7. It's affordable and clean energy, and that includes even things like carbon-based fuels that, you know, people who are cooking all over the world, in the developing world, are cooking with these really foul fuels that emit, and if they could cook with clean fuel, that would be fantastic. But electricity is right in there. So storage is the key enabler for this. First of all, if you want to talk about massive deployment of wind and solar, these are intermittent, and therefore they can't by themselves be fully integrated into base load. So that means if you don't have storage to bridge the gap when the sun doesn't shine and the wind doesn't blow, then you're going to have to back this up with some carbon-fired, whether it's diesel or gas or what have you, and it's going to give you the most expensive electricity, as we can see in Germany right now, the most expensive electricity in Europe, and with all of the so-called sustainability. So I mean, nobody wants that. And let me tell you, renewables minus storage is not a solution, because the way that the grid operates, supply must be in perfect balance with demand everywhere at all times. So the electricity powering the lights here was generated just moments ago. If all of a sudden we have abundant excess electricity that's generated by solar and it exceeds the demand, you can't do anything with it. If you generate it, it goes in the wires and the line voltage goes up. And can you imagine if instead of plugging in, what are you supposed to be here, 220, 240, what's your voltage? 240. So instead of 240, you get 260 or 265, you'll blow up your devices. And if the supply doesn't meet demand, well, we all know what happens there. You go to brownout conditions. So you have to have storage. And what you're looking at here is the world's largest supply chain with zero inventory. And today's grid is so crazy. We have generation capacity sufficient to meet peak demand. And peak demand is about a third to half more than average demand. So you've got all this capacity sitting there idle about 98% of the time. If you had storage, you could shave off the peaks and you wouldn't have to build new plants and so on. So you say, well, it sounds like I made a compelling case for storage, so why don't we have it? Maybe it's because what, just the dummies go into electrochemistry? Is that it? No. No, it's because this is the toughest problem. How tough is it? Long service lifetime. Forget your phone. Your phone, you toss it about every 2 years. Does anybody here have a 10-year-old phone? No. Anybody have a 10-year-old phone? Somebody once said, I do. And I said, did you have the original battery? Of course he doesn't have the original battery. All right? So we have to have a battery that'll last decades, not months, decades. Safe. Lithium-ion batteries catch fire. If it's a single phone, it's a bad day for a single passenger on an airplane, scares the rest of us, but, you know, so what? It's just one phone. But imagine a battery the size of this auditorium, lithium-ion, it catches fire, it's spectacular. Operationally flexible. The grid has there's 17 different electrical functions on the grid. Some of them are short duration, things like frequency regulation. Then there are things like load leveling, load following, peak shifting. I mean, these are long duration. So you have one set of applications that are more like a sprinter, and the others are more like a marathoner. You know, the person that can run 100 meters in 10 seconds doesn't run a marathon in an hour and 15 minutes. That person probably couldn't even finish the marathon because it's a different kind of training. But the battery that can power a hearing aid can't power an electric car. But this thing has to do everything. Or else you're going to have different batteries for different functions, and that's going to be really crazy. But this is what kills it. It has to be super low cost. How low? It's not battery versus battery. So don't ask me about flow batteries or other stuff. None of them work. None of them work in this application at the price point. It's battery versus combustion. It's battery versus gas. It's battery versus diesel because hydrocarbons are ubiquitous and heavily subsidized and deeply entrenched by corporate interests that don't want to just willingly go away and say, we've had our day and it's great to see this zero emissions generation. They're going to fight to keep it. So when I started working on this around 2006, 2007, I reasoned that if cost is what's preventing widespread deployment of storage, I have to invent to the price point. And I reasoned that the classical approach in the university doesn't work. The classical approach is you get your research grant and you invent the coolest chemistry. And you publish in the best journals you can. You build your career and maybe you'll spin out a company. That will work. They'll chase down the cost curve, but they won't get low enough in this market. So if you want to compete against hydrocarbons, you have to think about cost on day one, not day 1,000. So that changed everything, the way I thought about it. And before I launch into this, I want to have this last comment about by way of introduction. Let's not forget that the battery was invented at the university by a professor. It did not come from a corporate lab. It did not come from the national labs. It came from the university, like here. So when people talk to me about, oh, what about the DOE national labs? I say, they didn't invent anything. Volta gave us the first battery. Here it is, a stack of coins, silver and zinc separated by cardboard soaked in brine. With this invention, he gave birth to a new device and a new field of science, electrochemistry. And in addition, without any innovation hubs, without any Silicon Valley venture mentoring, or any of this blah, 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 this, within 10 years, migrated off campus and gave birth to new industry, electroplating and electroforming. And I submit to you, in 1810, they were already here in London, Sir Humphrey Davy, electroforming. And people tell me, have you heard about 3D printing? 3D printing, they were doing it here in 1810. But you know, the other thing that Volta's discovery did was, for the first time, it demonstrated the utility of a professor. Until Volta, nobody imagined a professor could be of any use. But Volta showed that if you give a professor resources and leave him alone, I mean, good students and so on, he's liable to do something of societal value. And I've always said this, right? But I was on my feet giving a talk like this, and all of a sudden I was hit with this epiphany. You know what this man did with this invention? This is the beginning of the electrical age. What do I mean by that? Before Volta, the term electricity applied to what? It applied to static electricity. Before Volta, electricity was static. You could take a piece of amber and a piece of wool and rub the amber and build up static electricity, and then put a piece of straw on a cup of water, and then by moving the amber, you could redirect the straw, which was absolutely fantastic in 1650. The concept of action at a distance, the notion that you could move something without physical contact, that was the first time demonstrated by static electricity, but that was it. With this, for the first time, you have electrons in motion. A battery is not a voltage device, it is a current source. Electrons in motion. Only electrons in motion do work. Electrons, you know, you say the same thing about people. I could say about the student, oh, he was a fine young man, full of potential. All voltage, no current. All right? So with this thing, for the first time, you can perform electrical work. And everything we see here, everything we have today, starts with this. That's how powerful this invention was. And you know, Faraday here. Faraday had to be a good electrochemist, otherwise he couldn't be a good physicist, because the only way the physicist could generate current was with electrochemistry. So if you were an incompetent electrochemist, you couldn't do any experiments. And that was with this current going through a wire that they detected a magnetic field. And then somebody said, well, if a moving electric current gives rise to a magnetic field, then somebody said, what would happen if we took a conductor and subjected it to a moving magnetic field? And they discovered that it generated a current, and that gives birth to the dynamo, and here we are. But everything starts with this. It's fantastic. By the way, that note, I didn't scan this and grab it off the internet. I had this note in my pocket. This is my note. I don't know what happened to it now, but I did a very high definition scan of it, and I'm proud to say that. I didn't just go and grab stuff off the internet. You have to know the provenance of all this stuff. Anyways, all right. So what's the path forward for storage? So first of all, you have to confine your chemistry to earth-abundant elements. So here's a chart. It shows the relative abundance of the elements in the Earth's crust as a function of atomic number. And we see up here, it's a semi-logarithmic plot. So you see up here the abundant elements. They're the low atomic numbers. And you see down here the scarce elements. They're typically the high atomic number. And mandate that I gave to my students was the difference between the abundant elements and the scarce elements is 1 billion times. 1 billion times. So I told them, if we're going to build a battery that's going to scale for grid level storage, they are forbidden to go to the lower part of the periodic table. I mean, look at tellurium. Tellurium is about as earth abundant as gold. I don't know why people work on cadmium telluride solar cells. I don't care that they're more efficient. There isn't enough tellurium in the Earth's crust to scale. The only reason you would work on those would be to learn something fundamental, but ultimately, if you're talking about something that's going to change the energy landscape, you better be working on something up here, or else it's not going to scale. Look, silicon is what we make our photovoltaics out of. Silicon is why it's the second most abundant element in the Earth's crust. That's why everybody here has one of these in his or her pocket. If the semiconductor were made out of rhodium, nobody would have one. Right? Oh, by the way, I got to tell you, because you understand this. You know that expression, connect the dots? You know, it's business school, the business, you know, we're going to connect the dots. Really? You're going to connect the dots? All right, well, let's look at this. Lithium is atomic number 3. Beryllium is atomic number 4. This is from a government publication, by the way. Why would you connect lithium to beryllium? Do you know of anything that has an atomic number of 3.4? Even if you made a beryllium-lithium alloy, all of the lithiums are atomic number 3, and all of the berylliums are atomic number 4. What does this mean? What's crazier? That somebody drafted this, or that somebody published it and hasn't been taken down? It's still out there. This is from the U.S. Department of Energy. I call it the Department of Entropy, but anyway. All right. Oh, okay. So I say if you want to make something dirt cheap, you should make it out of dirt, and preferably dirt that's locally sourced. Because it doesn't make sense to trade your dependence on imported petroleum for dependence on imported neodymium. You know? Instead of burning oil, we're importing neodymium from China. Money's going out of the country either way. And make it easy to manufacture. Design at the discovery stage. It has to be primitive and easy to build. Why do they call it the gigafactory? It costs $5 gigadollars. $5 billion to build that stupid battery plant in Nevada. You know what I could build for $5 billion? 2, not 1, but 2 integrated steelworks, each producing 2 million tons of steel per year. Instead, I get 1 battery plant that makes yesterday's lithium ion cells, the 18650s. And people say, wow, is that ever cool? Just so stupid. All right, so let's pose the right question. Look at the question I posed. Inventing a colossal cheap storage device. I did not use the word battery. If I use the word battery, I start thinking about a right circular cylinder like the one that's powering this remote control here. And I start thinking, so how do I take those little 18650s and make them big enough to fill this room and give me some megawatt hours of storage? I never did that. I just said, keep it conceptual. And by the way, disregard to conventional wisdom. Do not consult with the incumbents. And that goes for anything. I would never talk to any battery experts. If I did, they'd tell me all of my aspirations were foolish. Everything that could have been tried has been tried. What I want to do won't work. I looked outside the field. I disregarded conventional wisdom. So I looked for inspiration outside the field. My other area of research, what I've been doing at MIT for the first 25 years, was working on electrolytic production of metal. So I looked to an aluminum smelter. Here's a modern aluminum smelter. This is from Canada. It's the Alouette in Quebec. From left to right, it's probably about 25 meters. And then from front to back, it's probably about 2 kilometers. And this thing's making aluminum nonstop, 24/7. It's probably 500,000 amperes, 4 volts. There's a man. You see a man in the corner there? Yeah. That gives you a sense of scale. And this thing produces aluminum nonstop, using huge quantities of electricity. This was invented in 1886 by two men working independently, Charles Martin Hall in the United States and Paul Héroult in France. There they are. Héroult's on the left and Hall's on the right. They were both born in the same year, and they both died in the same year. And they met once in 1911 when Hall was getting the Perkins Medal from the American Chemical Society. And Héroult came from France and spoke in praise of Hall. And they were fierce competitors, but they respected each other. They both patented, and the patents crossed at the World Court and cross-licensed and so on and so forth. It's a remarkable story, two guys working independently. Well, they were both born in the same year, so by my math, they must have been the same age in 1886. So how old were they? 52, 42, 32, 22? Yeah, 22. Two 22-year-olds changed the world. With this invention, they turned aluminum from a precious metal costing more than silver into a common structural material. 22. Anybody here over 22? What have you done? Huh? What are you waiting for? They go from dirt to metal for less than $1 per kilogram. That's a modern miracle. So I looked at this thing and I said, man, that thing goes from dirt to metal for $1 a kilogram, and this thing traffics in huge amounts of electric current, except it's a consumer of current. I said, if I could figure out how to teach this thing to store current, at the end I'll have something that's big and cheap. Everybody else is trying to figure out, how do I take this little stupid thing and make it big? And I'm saying, this thing's already big and it traffics in current, just teach it to store. You see, that's the different way to pose the question, by analogy. And there it is, the liquid metal battery. So it's got three liquid layers. The top layer is a low-density electropositive metal. The first embodiment was magnesium on top. And then the opposite that, so that's a really good metal, a really good electron donor. And then I want to put it against a really bad metal, but not a non-metal, because it has to be electronically conductive. Otherwise, things get really messy. So I want to have the best metal against the worst metal. That gives me the voltage. So the worst metal is down, it's on a semi-metal. So I put antimony. And in between, I got a molten salt electrolyte. It's high temperature. Can't use aqueous. But mercifully, magnesium is insoluble in the salt, and the salt is insoluble in antimony. They stratify, just like salad oil and vinegar, only now you got 3 layers. So we can make a demo. We can put salad oil, vinegar, and mercury. We have 3 layers. Serve that up. And I don't need any membranes, no separators. And so what happens is that on discharge, the magnesium wants to alloy with the antimony, but the magnesium's insoluble in the salt. If the magnesium becomes magnesium ion, the magnesium ion can go through the salt, and then the electron goes through the external circuit where it does work, and down here it recombines. So the top layer gets thinner, and the bottom layer gets deeper. And then to charge, we force current through and electro-refine back. So the magnesium goes back to the top. We restore the top layer, purify the magnesium, purify the salt, purify the antimony, return the battery to its pristine condition. Now, as the current flows, either on discharge or on charge, it generates heat. And that's a threat in a lithium-ion battery. Here, we take that threat and we turn it into an attribute. We trap that heat. So imagine 4 hours discharge, generate the heat, it sits for 8 hours. At some point later in the day, 4 hours charge, 8 hours rest. With that kind of daily cycling, you can keep this thing at temperature. Who did the work? These are my students. They're young. They're graduate students, undergraduate students, postdocs. Almost all of them had no background in liquid metals, molten salts, or electrochemistry. I brought in novices. They're bright. I mean, they're at MIT. But they weren't steeped in the field. I brought not the expert. I brought the anti-expert. And a multinational. She's from Spain, Korea. They're from China. She's from France, Trinidad. You get this one? French Polynesia. He's from Tahiti with a PhD from Paris in high-energy physics. and then came to me. Poland. David and I were both born in Toronto in different years. And I hired a few token Americans as well. So that's the team. And I'm the only one that was really steeped in molten salts, liquid metals, and electrochemistry. So I taught them how to think about the problem and then turn them loose. And the first year was terrible. I mean, we were getting beat up by the sponsor for really poor progress. But they learned, failed, and then second year, better. In the third year, they'd work miracles. And my initial funding came from the French energy giant Total, and then we got first round funding from the ARPA-E division of the US Department of Energy. And with that, I was able to bankroll this group of 20 people for 3 years. It was a fantastic time. So here's an example. This is a cutaway of an early cell. The top is the magnesium. Obviously, it's frozen now at room temperature. And then the salt, and on the bottom is the antimony. And this is Steve Chu, who was the Secretary of Energy at the time, visiting Jocelyn, one of my students. And he came down and he autographed the glove box. So I know he was there on June 22nd, 2012. And I showed you magnesium, but there's a plurality of choices. And so for the top layer, it can be any of these electropositive metals. And we've looked at various combinations of them, and they all work. They work beautifully. And the bottom layer can be any combination of things like this. And there's even other possibilities as well. So it's a platform, really. We've tested over 1,000 cells, many chemistries. What are we looking for? Different alloys, different salts. You say, why don't I just go to the database? The database is very spotty. When it comes to liquid metals, we know a lot about steel, a lot about aluminum, a little bit about copper, magnesium. But you look up even something like the phase diagram of antimony bismuth, and you'll either find nothing or you'll find two phase diagrams that don't agree with each other. So we had to go and measure all this stuff. And this isn't just cook and look. I mean, we managed to get this paper published in Nature, and you don't need to be told what Nature represents. This is really tough. And it launched the careers of the young people. I mean, I have tenure. Tenure means never having to say you're sorry. I don't have to publish. But I do. Why do I publish? What, to tell other people what I'm doing? No. The reason I publish is for the young people, to launch their careers. That's why I publish. I don't care if I publish at all. For me, I don't care. All right, so here's we got. It's earth-abundant elements, self-assembling, easy to manufacture. The round-trip efficiency, pay attention here. People, if you read on the internet, the people, they say I'm crazy, this is all nonsense, it can't possibly work, that it's going to burn. It doesn't burn. Magnesium doesn't burn. It burns as pyrophoric ribbon or in fine powder. But have you ever been to a magnesium smelter? I have. They open up the top and they pour magnesium in air. So don't tell me that magnesium burns. People who say that, they missed a day of school. Now, the round-trip efficiency, 80%. That's after allowing for the losses due to the heating. Now, if you look at pumped hydro, where you have a dam, you pump up high, and then store it, and then let it fall down, round-trip efficiency on that is 70%. Now, I'm not going to say 80 is better than 70. I'm just going to say that this is comparable to pumped hydro, and that's the #1 form of energy storage at grid level. So it's fine. It's self-heating at commercial scale, immune to thermal runaway. What's the worst thing you can possibly do to this? And we did it by accident. It wasn't planned. No animals were killed in the process. Somebody goofed and something fell into a cell. It was an open cell inside a glove box and caused the magnesium to mix with the antimony. So you get a giant exotherm. And the temperature went up below the boiling point of anything in the cell, below the melting point of the steel container. So we knew then and there that you could shake these things all you want. You cannot have anything give you trouble in thermal runaway. And it's safe to ship even by air. You can't ship lithium-ion batteries by air. These things I called the Department of Transportation, and I wanted to get a reading on this. And they said, what's the voltage at room temperature? And I said, room temperature, it's solid metal and solid salt. There's no voltage. It said, you can ship any way you want. But this is the most important thing. This is something that people don't ask the lithium ion people. Capacity fade. All right, so let me show, these are cells. This is the percentage. 4.5 years at temperature. The temperature for these cells is 475 degrees Celsius, 475 Celsius, 5,000 deep depth cycles, 100% charge to 100% depth of discharge, 5,000 times. If you did that once a day, that would be tantamount to 13 years. There it is. 99+% retention of capacity, no fade. I didn't make this up. This isn't the one cell, and they all others die. They all do this with all of the chemistries, right? Nobody can do this. So 2 of the fellows in that image, they came to me and said, we want to start a company. Now, I was not involved in startups prior to this, because I'm a professor, and I valued being a really good professor. Right? But they said, no, we got to start a company. Why? Because if we want to change the world, we can't just file patents and write papers and hope that somebody takes a license on this. They'll fail. So that hooked me. I do want to change the world. For the better, I hope. All right, so all the catchy names were taken by 2010. So we gave them the name, the Liquid Metal Battery Corporation. Terrible name, boring, but so what? And then a couple of years later, we changed the name to Ambry. How did I get the name Ambry? I came upon the fact that, you know, there's this company out of the Bay Area called Cisco Systems. They make routers. I found out that they were called Cisco Systems because they were based in San Francisco. So I took a look at the word Cambridge, and I said, because I invented the battery in Cambridge, the other Cambridge, Cambridge, Massachusetts. I know there's a Cambridge around here somewhere, but anyway, whatever. You know. Anyway, so Series A funding came from Bill Gates. Now, I'm Canadian. I'm very polite. I wouldn't go after Bill Gates. Bill came to me. He did. Why? Because he, too, was watching my chemistry lectures online. And so in the summer of 2009, I got an email from a woman who said she was his secretary. He just stepped down as CEO of Microsoft. And she said, Mr. Gates is coming to Boston at the end of September. He'd like to meet with you for 90 minutes. Would you have time? Well, I ignored the email because I thought the students had hacked into my account. And I said, you're not going to make a fool of me. I'm not going to answer that. And then about 10 days later, she wrote again and said, maybe you didn't see this, but he really would like to meet you. So I showed it to a few people, and they said, I think this is real. So I wrote back, and then finally, I said, what's this all about anyways? And then he wrote, and this is what I want to talk about. And he came, and we sat in my office. I just lectured 3091 that day. It was a Friday. We sat in my office for an hour and a half. And we talked about computers in education, distance learning. He even made some comments about the camera work in 3091. He says, you got to improve that camera work. And then towards the end, he says, so what are you working on? And I sketched out on a whiteboard this idea of the liquid metal battery. And he said, you know, it seems to me that the fundamental approach to grid level storage ought to be intrinsically different from the approach to mobile storage. And I said, you're smart. I said, I got colleagues here that are trying to repurpose lithium-ion batteries for grid-level storage. And he said, if this thing ever gets spun off a campus, let me know. I'd be willing to put some money into it. And so a year later, 2 of my students went and visited him, and he became our first investor. And so I met Bill Gates, not because I wrote an op-ed piece for the Wall Street Journal. I met Bill Gates because I was teaching a big freshman chemistry class, which all of my colleagues would kill to avoid, because nobody wants to teach a big service class. But I went there. Why? Because why teach 500 people when I could, forgive me, why teach 50 people when I could be teaching 550? I went for maximum impact. And then they couldn't fit everybody into the auditorium, so then they had to record the lectures, and then by 2004, we could stream video over the internet, and next thing you know, he's watching my lectures. So, I can't make this stuff up. Yeah. All right, and then Total matched him. So Total sponsored the research on campus, and Total also invested in the company. And that's how it began. So this is what it looks like. We're out in Marlborough, Massachusetts, about 40 kilometers west of Boston. These cells are 10 centimeter on edge, and each cell is about 80 amp hours. And then we're also looking at doing 4 times that. So that would be 20 by 20 centimeters. And that would give us more than 4 times because you don't have the boundaries, up to 380 amp hours. And now we've got, starting this year, a tall form, 1 cell, 800 amp hours. Now this, I put this on the same scale. This is a 3 amp hour lithium ion. This is what they make in the Gigafactory. It's the 18650. It's 18 millimeters in diameter, 65 millimeters tall. The 0 means that it's a cylinder. Yeah? So that's an 18650. Now why is that important? If I wanted to put 1 megawatt hour on a 50 square meter footprint, I would need almost 100,000 of those little cells. So I don't care if I give them to you for free. You still have to pot them, connect them, balance them, and on and on and on. Whereas we would need 1,500 cells. So 1,500 cells is manageable. 100,000 cells? That's crazy. Do you know how many 18650s are in a typical Tesla? 1,000? 4,000? About 8,000 cells, about 8,000. All right, so this is what we're building right now. This is, we decided that the thing should be able to be shipped along the road. So that's going to make shipping container as the footprint. So this is 1/4 of a shipping container. Shipping container is 40 feet long, so this is 10 feet, and the cross section here is 8 feet by 8 feet. So this is 18 cubic meters. This will give us 1 megawatt hour, 1,000 volts. This thing weighs 15 tons, very heavy. The energy density is poor compared to lithium ion, but this thing isn't supposed to move. It doesn't matter. Don't pay for attributes you don't need. Besides, I say that thing's so heavy no one can steal it, so it's got its own anti-theft built in. But the thing is, it must be priced below that of lithium ion. And why is that important? There's a term of art, it's called premature lockin. It's what happens when a new technology comes into the market and there are different purveyors. Now, many of you are too young to remember when video cassette recorders came out. There were 4 different formats. And then it came down to 2, VHS and Betamax. And Betamax was superior, but VHS got the jump because it was a 2-hour cassette and the Betamax was a 1-hour cassette. Why was that important? Because with a 1-hour cassette, you could watch 2 30-minute sitcoms, but with a 2-hour cassette, you could put an entire movie. And no one anticipated. The idea was that you would record programming from your television. No one imagined the idea that you could take a license from the producer of a film, copy it onto video cassettes, and so on and so forth. But anyways, the VHS took over. That's called premature lock-in. Well, maybe we're going to see the same thing with lithium ion. Now, this chart was put together by Bloomberg New Energy Finance. And what they did is they took the prices of lithium ion from 2010 down to 2016, and they fit them to a semi-log plot. And based on the coefficient, they called it a 19% learning rate. It's just the fit of the historical pricing, all right? It's largely driven by Chinese overcapacity. It's not learning, but anyways. And then these Barbie dolls, look at what they do. They take this curve and they extend it out to 2030. They took 5-6 years and extended out for another 14 years and announced that it'll be $73 a kilowatt hour by 2030. Meanwhile, I'm trying to get this company off the ground. So our investors come to me and say, you guys are toast, because you see, we started with lithium, lead, antimony. which at scale would have got us to $270 a kilowatt hour when lithium ion was 1,000. So we were beating lithium ion so badly it wasn't a joke. But look what happened over time. Lithium ion comes down, so we pivoted and went to lithium bismuth. Why didn't we go to lithium bismuth first? Because bismuth was too expensive, but a new mine opened up in Vietnam. In 2014, the price of bismuth dropped to half, and now we jumped to lithium bismuth. So now we're going to go to 170, but the lithium ion keeps coming. And by the way, this is lithium ion price. So price could be below cost to drive out competitors. And these guys, I say, look, are you talking about cells or are you talking about batteries at scale? And they don't know. They don't know. I'm being asked to compare my all-in battery at 1 megawatt hour scale to this guy's little flashlight battery. It's really crazy, but it doesn't matter. This is what drives decision making. So we pivoted again. Now we've got Chem C. I can't tell you what it is just yet. And Chem C on day one is putting us at $75 a kilowatt hour. And they'll never get to $75 a kilowatt hour. So that's where we are. But it's been tough. And what's our learning rate? We're smarter than they are. All right. Let me show you some other fashionable nonsense. This is from California Independent System Operator. One of my colleagues actually presented this. And it says, grid storage spans 3 orders of magnitude in time scale. 3 orders of magnitude. Daily cycling, weekly cycling, monthly cycling, yearly cycling. Do you really believe you're going to put the capital into a battery that you're going to use once a year? What are they doing with this? And so there's this whole buzz right now about long duration storage. What do you mean long duration? Like sunset to sunrise, that's the long duration. Or maybe 2 or 3 days, it's been raining, you haven't been able to get much solar energy. But the notion that you're going to take it from July and save it until a day in December, this is stupidity. So what are they showing? New long duration cases, monthly, yearly, seasonal. You'll see this. And people parroting right up to the Department of Energy offices. And I'm saying, what are you guys doing? So what this shows is that if you're going to have, by the way, so you want to have the electricity after it goes in and out of your device contribute on the order of 2 or 3 cents a kilowatt hour. Let's say it costs you 10 cents a kilowatt hour to generate it by sun, and you're going to store it. And now it comes back, and as a result of being stored and coming back, now the electricity costs you 25 cents a kilowatt hour. You're going to say, what are you talking about? You want to be able to generate it at 10 cents a kilowatt hour, and for having stored it and then pulling it back out, it adds maybe 2 cents a kilowatt hour. So now it's 12 cents. It's still solar. It's still cheaper than what you would have got by coal. All right, so if you, pardon me, if you want to do 2 cents a kilowatt hour and cycle it only once a year, you're going to have to build this battery at a capital cost of 20 cents a kilowatt hour. I mean, this is crazy. 20 cents a kilowatt hour? What's crazier, that they put it up, or that somebody read it? And I saw the video of this. This is a YouTube video, and all these people are sitting there politely clapping. It's just unbelievable. No one stood up and said, "What are you doing?" Anyways, so we're now trying to raise some money, Series C++. We need about $25 million for the next 2 years, and then get the final product out. We cannot release a product that doesn't work. If it fails prematurely, we're dead. And by the way, the industry won't take anything. You understand the Arrhenius equation and so on and so forth. They don't know any of this stuff. They say, if I claim that I can go for so many cycles and so many years, they want to see the data, so many cycles and so many years. So if I can make the claim that I can run this thing for 5 years, I got to give them 5 years of data from the big thing? Man, those are high standards. All right, so we've got 2 more years, and then I think we're done. You may have heard of this company, GE. So back around 2006, they came to MIT, and I pitched a liquid metal battery idea to the vice president of research for entire GE. He didn't react because they were already committed to Durathon. Durathon is the old Zebra, sodium nickel chloride. And after 10 years, $1 billion, at one point they had 400 people working on it, they quit. They failed. Why? It's not cost effective to manufacture the batteries at a competitive price point compared to other battery technologies, which is to say, when they started in 2006, lithium ion was around $1,200, $1,300 a kilowatt hour. They figured they could make Zebra for about $350, but by 2015, lithium ion was below that. So they got cut off by lithium ion, burned. If GE with $1 billion in 10 years can't do it, and I've got $65 million in 7 years and we're still in the game, watch us. All right, so what's next at MIT? We're still looking at next generation chemistries, lower temperature, higher voltage, lower cost, and I'm now starting to think about cars, because I know lithium ion is no good for cars either, but it's not going to be this one. So this is Zebra. This is the one that failed for GE. So it's liquid sodium contained in a cup of beta alumina. And then on the other side, you've got a molten salt electrolyte, and then the positive electrode is nickel chloride. And the problem with this thing is that you've got this fragile, brittle membrane, because that thing has to be paper thin, otherwise you're going to have a big voltage drop across it. But if it's paper thin, it's going to be mechanically weak. So this is the tension. You want to make it thick to be strong, and you want to make it thin to be non-resistive. And the nickel chloride is a solid-solid reaction. The kinetics of that are terrible. So what we did is we started working on this about 2 years ago, and we came up with a different way to allow, I call this chemistry a displacement chemistry, because sodium and sodium chloride are running one reaction, and nickel chloride are running another reaction. It's a displacement reaction. So we figured out how to run a displacement reaction without a brittle membrane, no ceramic membrane. It's a metal mesh, and it uses a different principle. And this was fantastic. It was a big surprise. So now we could put not just sodium, it has to be sodium in the Zebra battery, because only sodium is the ion that will transport through beta alumina. But we could use lithium, sodium, magnesium, calcium, anything up there. And then the molten salt. And on the bottom, we don't have to use nickel chloride. We can use lead, antimony, bismuth, tin, zinc. And so there's a whole new set of opportunities. This is different from liquid metal. This is called liquid displacement battery. It's the LMB is liquid metal battery. LDB is liquid displacement battery. When I first started typing LDB, the spell checker kept putting LBD, little black dress. And I said, no, this is liquid displacement battery. And I had to teach my dictionary that LDB in caps is okay. I'm not writing about dresses. And this is going to be higher voltage, about 3 times the voltage. Okay. So I see we're getting close to the end. So I'm going to jump over. We're not going to go through all of this other stuff. I got too excited. I prepared too much stuff. So it's okay. It's okay. So now what we're going to do, we're going to zip down to towards the end. Yeah. That's Boston Metal. That's it. Okay, good. Now we go right here to the end, because I want to make sure that I've got some virus on the machine. Okay, it's all good. I don't have my glasses on. I can't see anything. Is that it? Where? Oh, I have to go up to here. Oh, what happened? Don't let anybody over 30 touch a computer. Now we'll go to this. Yeah. All right. So I've shown you that this odyssey with the liquid metal battery, what do we learn? We learned about the power of contrarian thinking. We learned that everybody says go to room temperature, that's going to be most energy efficient, and so on and so forth. I said, no, I went to high temperature. The high temperature gives you the fast electrode kinetics. And fast is everything. Right? They said, go with experts. I said, no, don't go with experts. Go with the anti-experts. I brought in the novices. So these are the kinds of lessons that I learned from this experience, and I invite you to think about. And the other one is about going global. The Apple experience, build everything in one factory in China, in Foxconn, and then ship it all over the world. I'm saying no. These batteries are big, they're heavy, and they're based on earth-abundant elements. So instead, batteries in Africa should be built in Africa by Africans using African resources. That way they become authors of their own future. Batteries in India should be built in India. Batteries in North America should be built in North America. That's very different. Have aligned interests. So that's the message that I'm giving you. And see, it's all liquid metal. Liquid metal is fantastic. And the last piece that I'll say is that when I'm with the students, I always give them the battle cry from Paris, 1968. Soyez réaliste, demandez l'impossible. Be realistic, ask for the impossible. And sometimes, with enough ingenuity, the impossible becomes the inevitable. Thank you.
Okay, so I think we've got time for a couple of questions. If anyone's at the back, yeah. There's a microphone heading your way at high speed.
Hello. Yeah. First of all, thank you very much for your talk. I'd like to ask about the discharge capacity of your cells, because you've mentioned how it compares in terms of storage with lithium ion. You've also mentioned pumped hydro storage energy. But how does the discharge rate perform? Because if you want to use this into large-scale grid electricity storage, it's just you need certain discharge rate to be able to supply the energy fast, right?
So the discharge rate, the rate capability is very high. We can discharge these things at multiple C, and the other thing is that they can take a lot of abuse too. So, you know, you can get paid sometimes to actually accept electricity, because sometimes the demand falls, supply is exceeding demand, and the operator is looking for some place to dump electricity. That's where they go to negative pricing. They invite factories to turn on all their machinery and so on. This thing, you can force huge currents into it. And you could do it with lithium ion, but you damage. By the way, if anybody's got a car with lithium ion battery and use those high-speed charging stations, you can use them, but they really shock the battery. So you're taking the battery closer to death sooner. But this thing, we've done it and then gone back to normal cycling and no evidence of any damage. So they can go to multiple Cs. It's fine. Yeah. That was one of the things that drove us to the all liquid, that it could respond very quickly. And it doesn't suffer any damage. You see, in the lithium-ion battery, you have solid particles in the positive electrode, and over time, you know, when it lithiates, they expand, and then when they delithiate, they shrink. And if you do this 100 times with a piece of ceramic, eventually it fractures, and then the one piece is no longer connected. So that's how you lose capacity.
Thank you, Professor, for the talk. It was really insightful. Mine was slightly less technical, my question. It was more about what you were saying about getting anti-experts in when you want to innovate. Do you think it's worth anybody here who wants to do something new to to get experience in that field, or do you think that could be detrimental?
I don't have any formula to give you. In this instance, for me, bringing on novices was a smart thing to do in retrospect. I didn't know at the time. But all I'm saying to you is that if you have a certain desire, you want to make the world a better place, you want to take on a certain challenge, don't edit yourself. Don't say, well, I was never any good at chemistry, I can't possibly work on this. No, you might bring a fresh perspective. You know? So I don't have an answer. It's all visceral. I don't have a plan. People say, what's your plan B? I said, I don't have a plan A. If I had a plan A, I wouldn't be here, because everything would be all mapped out, and I have to be able to respond.
One more question.
Gentleman in the middle there.
Do you think we exhausted all the hydrometallurgy way of making materials for energy at room temperature or lower? Lithium phosphates, these multiferics, these complicated materials. Do you think there's a chance we could, put together materials still, which would, or this is the high energy route is the only one we should?
Well, the question is, what happens if you use hydrometallurgy and put together things like lithium iron phosphate and so on? And I think that for grid level storage, I don't think it has the intensity.
And that's because of the expansion.
Well, the solids don't like to undergo these transitions. I mean, the good news is that John Goodenough, who was at Oxford in 1985, made the discovery that lithium cobalt oxide would intercalate lithium ion. That was an important discovery. But he never then wrote the prescription for batteries. And the fact that it undergoes this volumetric excursion, that makes it problematic. But we pressed on, and here we are today. Now, when you go into grid level storage, just look at the aluminum smelter. Look at the aluminum smelter. That's 500,000 amps at 4 volts. You can't do that with solid. You can't. So, but, I don't want to negate anybody. If there are people here working on solid-state batteries and you make it successful, I'll be the first to congratulate you. But I'm just telling you, from my perspective, I just say high temperature, all liquid. Liquid metal, molten salt.
Thank you for your talk, first of all. I wanted to ask you if you think that a good scientist is also a good teacher.
No, I know a lot of good scientists who are terrible teachers, so yeah. But I think that there's the surprise for me. The surprise for me is that all of this stuff that I showed you today with the liquid metal battery and then the liquid displacement battery and so on and so forth, all of this was not from advanced chemistry. My degree was in metallurgy. I did not have a degree in chemistry. So I didn't use density functional theory or computational none of that stuff. No VASP, none of that. All of that stuff is useless when it comes to liquids. It can do vapor and it can do solids, but it can't do liquids. So how did I get to this? I got to this because I was a metallurgist from University of Toronto, and therefore I did not know any chemistry. Metallurgists historically don't know chemistry. Why? Because they're not taught chemistry. Why? Because it's purposeful. The reason is that if you're a chemical metallurgist, if you're going to make steel, you start with iron oxide, you react it with carbon in the blast furnace, and you make pig iron and so on. If you're going to make aluminum, you start with aluminum oxide, you dissolve it in cryolite, and you pass current, and then you make liquid aluminum. If you want to make magnesium, you start with magnesium chloride, you electrolyze, and so on. So every one of the metal production processes is prescribed based on the availability of the ore, of the feedstock. So the first chemistry class that a metallurgist takes is thermodynamics, Gibbsian thermodynamics. So now we say, okay, is this reaction going to go to the right or to the left, and so on and so forth. Now, today, modern material science is a carte blanche. So, okay, so you know how to use Gibbsian thermodynamics, but what's the reaction you should be considering? They don't know. They don't know. Now, I came to MIT and I was thrust into teaching as an assistant professor in this freshman chemistry class, electronic structure and bonding. I didn't know. I had to teach myself. I was about 12 hours ahead of the students, and I was just, and I wasn't doing the lecturing. I was just doing the Q&A. We had 3 lectures a week and 2, they call recitation sections. It was basically Q&A. So I was essentially a junior faculty acting as TA. So I had to learn this stuff. And then, around 1993, I took over the lectures. And then I had to master how does a first-time learner who's 18 years old, smart, but hasn't seen this stuff before. And that trajectory of trying to take this simple stuff and present it in a way, and they weren't going to have any quantum mechanics, they didn't have any math yet, so we couldn't give them that. So you had to teach electronic structure and bonding without resorting to mathematics. And that clarified my thinking. So I invented all of this. I have a placemat on my desk. It's just a periodic table laminated. And I'm just looking at it. And then just saying, well, geez, you want to get voltage, you got to take something that's very electronegative and put it with something that's very electropositive, and started looking at melting points and boiling points and so on. So this is a case where the teaching drove the research. You know? So if you teach, if all you do is lecture in your own little specialty subject and just talk about the papers that you've written, you don't really challenge yourself, but you step outside your comfort zone and you got to stand up. You know, the lecture hall is one of the last, it's high wire tightrope, because anybody can ask a question and it's live. It's like going to the theater, only when you go to the theater, you have to sit politely, all right? It's like going to the theater, but you don't have to sit politely. Well, you should be polite, but you can ask questions. And you're up there writing away, and all of a sudden somebody asks a question, you look like, that's a good question. I don't know the answer to that. You see? So the lecture hall it's a fantastic place because everything is live. There's no hiding. And, you know, by the way, when you get the question, you've got to be honest, because they know right away. They may not know the answer, but they viscerally know whether I know the answer. And if I don't know the answer, I say, I don't know the answer to that. I'll check with some of my colleagues, and I'll get back to you. In the next class, I come back and I give the answer. As opposed to giving some evasive response, and then everybody says, don't bother asking questions. The guy doesn't know. And he's just going to give you some BS, and so don't bother. That's unvarnished honesty. Yeah. And it sort of clarifies everything for you.
Right. And with that, no more BS.
No more BS.
That's the message, the take-home message. Thank you so much, Don, for a fantastic talk. I've never heard so many laughs in an electrochemistry talk before. It's
good.
Fantastic. Thank you.